Good day and welcome to today's tutorial. So we are going to be learning about round of errors in numerical analysis, and we want to understand in this problem why is it that the absolute error, that the maximum value of the absolute error is always less or equal to 1 over 2 multiplied by 10 to the power of minus k, where k is the number of decimal places to which we round up an arbitrary decimal number n. So this video is going to be more of analytical, and we are going to be trying to do a lot of proofs, but I promise to walk you through step by step so that you will understand at the end of the day why absolute error is less than or equal to 1 over 2 times 10 to the power of minus k. In some other scripts, you will see absolute error is less than 1 over 2 times 10 to the power of minus k. So depending on the text you're working on, you might see any of these two, but once we finish dealing with today's concept, you will discover that you will be able to understand why it actually came about. So I know this is a question that you've always wondered how it came about, so hopefully you came to the right place, and I'm going to solve it for you right away. So solution. So we're going to begin by first of all assuming what n looks like. So n is a decimal number, okay? So let me, for convenience, give it an integer part of 0. So then it has several decimal parts, so d1, d2, d3, and it keeps on going. Then we have dk plus 1, we have dk plus 2, and so on and so forth. So this is n. So I want to round off n to k decimal places. That means I'm going to count after the decimal point up to k digits, and I'm going to round n at the kth digits, rounding off n. So this is the rounded off version of n asterisk or n star is equal to 0 points. We'll have d1, d2, d3, and up to the kth digits, which in this case is going to be dk asterisk. So why is it dk asterisk? I'm putting in dk asterisk because whenever you're rounding off a number, remember you're rounding to the kth decimal place. Okay, so the kth decimal place, the outcome of this number is determined by the nature of this guy over here. If this guy is 5 or greater, you have to cancel 1 and add it up to this one. Then if not, you just have to leave it that way. But I'm going to deal with the case where d of k plus 1 is actually what's greater than 5. So let me just draw a kind of structure for what our d of k asterisk will look like. So I'm going to solve one case and you're going to solve another case. So dk of asterisk or dk star is actually going to be dk plus 1 if our dk is, let me say our dk is greater or equal to 5 not dk, rather if my dk plus 1 is greater than or equal to 5. So what does this mean? That the value of this dk asterisk, which is the rounded up version of this guy over here, okay, this value dk asterisk will be increased by 1 if this value over here, which is dk plus 1, is greater than or equal to 5. Of course, you know the trick of rounding off, okay, around 5, although there are a lot of discrepancies, or let me say there's a lot of rules about rounding up around 5 exactly. I know those rules becomes less confusing when we exceed 5, that's 6, 7, 8, 9. If the number just after the 1, we want to stop the rounding off. If it says 6, 7, 8, or 9, you can easily cancel 1 and add it to the place where you want to stop. But if the number is 5 exactly, there usually is some rules or some suggestions by mathematicians as to how to round it off, but that will not be what we'll dwell on in this video. We'll just use the general assumption. What if my k plus 1 is greater than or equal to 5, all I just need to do is I'm going to dissolve all the digits from dk plus 1 down to the end of the decimal point, and I'm now going to add 1 to this value over here, which is dk. So this will be my dk star. However, if dk plus 1 is less than 5, so I'll just leave my dk the way it is. I'm not going to modify it, so my dk asterisk will be dk. Is that okay? So I have now gotten the rounded off version of my number n. Now I am going to be more focused on this particular row, which is the case where the digits after where we want to stop is bigger than 5 or is bigger than or equal to 5. So I'll leave you to attempt this one by yourself, which is still going to be easy if you can follow the things I'm going to tell you in this video. Now that we've gotten our n as 0.d1, d2, d3, and of course I'm using d1, d2, d3 and so on and so forth because these are decimal numbers. Decimal is base 10, so all these digits d1, d2, d3, they can be each between 0 and 9, 0 and 9, 0 and 9, to anyone you pick. So up to dk, then the dk plus 1 and so on and so forth. There's dk plus 2, dk plus 3, and the approximated version is now 0. Or the rounded off version, is d1, d2, d3. Then we are stopping at the kth decimal place, so this is my dk asterisk. Okay, so all the other digits has been neutralized. So I want to find the difference between n star and n, but I'm going to put it in absolute value symbol. So this difference, remember, in the rounded off value and the original value, we usually call it the absolute error, or we call it error. Okay, error is the difference between an approximated value and the original value, and absolute error is now when you encapsulate your error in absolute value symbol in mathematics. In mathematics, the absolute value symbol is like this. So this is the absolute value of x, which we normally see square root of x squared, or whatever you want to call it. But the absolute value of a number is just trying to determine the magnitude of that number. So if you give the absolute value of -2, is going to return 2. The absolute value of 2 is going to return 2, because typically, mathematically, the absolute value is just the distance of a number from the origin, which is 0. So even though you're having a number in the negative side of the x-axis, all we are interested in is the distance of that number from wherever it is to the origin, and that should give me the size of the number, not the sign. So absolute value never returns a sign, it's just giving you the size of a number. And there are different symbols for expressing absolute value. You see me in this series of videos using ABS ERR for absolute error, or delta x, delta y for absolute error, and so on and so forth. But I'm going to get used to all the symbols that we are using. But now the difference between the approximated or the rounded off value and the original value is our error. Then housing that error in the absolute value symbol turns it to absolute error. So this here is absolute error. So the absolute error is equal to, of course, then this version, which is 0.d1, d2, d3 up to dk asterisk, then minus 0.d1, d2, d3, then we have dk plus 1, dk plus 2, and so on and so forth, so wherever the decimal number stops. So for simplicity, I'm going to express these numbers in scientific notation. So to express this number in scientific notation, so this is what will happen to the right hand side. Of course, you know how to convert numbers to scientific notation. Like, let's say you have 0.5678, you want to convert it to scientific notation at this particular point. So it will be 1, 2, 3, 4. So you have 8. I'm sorry about that. You have 5, 6, 7, 8 times 10 raised to the power of -4. Okay, so 1 2 3 4, we stopped at the 8th position. Is that okay? And we are rounding off, we are converting the number to an equivalent scientific or exponential form. So that is what we're going to do to these numbers here to make it simpler to visualize. Okay, now this one is now going to be d1, d2, d3 up to dk asterisk times 10 raised to the power of minus k. Remember when we had 1 2 3 4, we are interested in 8, and 8 is the fourth decimal place. So when we converted it to this form, it's going to be times 10 raised to the power of 4, corresponding to the number of decimal places that you moved the decimal points. So the same thing will apply to this number over here. So only that we'll have d1, d2, d3 dot dot dot. Then we're also going to stop at the kth decimal point, which is going to be dk, but there's going to be a point dk plus 1, then dk plus 2, and so on and so forth, then times 10 raised to the power of minus k, then in the absolute value symbol. So let's see what this results to. So there's a rule in absolute value. I can see these two things are common between these two differences. So when you have something like this, absolute value of ka minus absolute value of kb, okay, as far as these are constants, you can just take the constants out. A minus b, still the same thing as you saying a minus b and multiplied by k. So I'm going to remove this times 10 to the power of minus k. So it's going to be like this now. So I have my d1 up to dk asterisk, then minus I have my d1 up to dk points, dk plus 1, and so on and so forth. Then you have times 10 raised to the power of minus k. So let's come to what is happening in these two numbers. So you have to recall that our assumption is that dk plus 1 is greater or equal to 5. So if dk plus 1 is greater than or equal to 5, then it means that my dk asterisk is still the same thing as my dk plus 1. Is that okay? Dk plus 1. That means whenever this number over here is 5 or bigger than 5, we just, in order to round it up to the kth decimal place, we just need to dissolve it, then put 1 to this guy. But if it's less than 5, we leave it. So that's the rule that I'm using for this particular one. So they are actually in essence trying to tell me that this dk plus 1 is actually just 1 time more than this guy, 1 unit more than this particular one, in such a way that, assuming this number is something like 5 6 7 8, that's the rounded up version, then this one will be like 5 6 7 7. Is that okay? 5 6 7 7, because you have rounded these digits to the kth decimal place depending on the value of this guy over here, and we are assuming that he's bigger than or equal to 5. So since he's bigger than or equal to 5, we'll cancel 1, and when we now put it here, it's now going to be, instead of 7 8. So you discover that whenever you subtract this and this, you notice that 1 will be the difference, right? But we're not going to do that right away. I'm still going to do some more stuff to simplify these decimal places, because you need to be able to visualize what is happening before we subtract finally. Now assuming that I have these two numbers like this, I hope you know I can still express it like this: d1 to dk asterisk, then minus, so this is d1 to dk. Is that okay? I'll open a bracket, then plus 0 points dk plus 1 and dk plus 2, and so on and so forth, times 10 raised to the power of minus k. Now see what happens in this particular place from here to here. So it's just as if I had a number 5677.923, which I can still express as 5677 plus 0.923 and so on and so forth. Is that okay? So you can split a decimal number to the integer part and the mantissa part, which is what I just did here. I splitted this guy to the integer parts, then the mantissa parts. Okay, so where dk plus 1 marks the beginning of the first digit of the mantissa, so you have it like this. So the reason I did it like this is for simplicity. When we're subtracting d1 dk asterisk minus, this will be d1 to dk, and this is now minus 0. dk plus 1 dk plus 2 dk plus 3 and so on, like that. So you know minus times plus is minus, so this is times 10 to the power of minus k. So remember we have n asterisk minus n over here. So let's see what the answer is going to be. So this is going to be this minus this. Remember we established that since dk plus 1 is greater than or equal to 5, then we are going to add 1 to this dk asterisk. So we'll add 1 to dk, so our dk asterisk is just dk plus 1. So in other words, if here is 5677, then here should be what? 5678. So 5677 minus 5678, is that okay? It's going to be 1. So if you do this guy minus this guy over here, you're going to get a 1 always. So this minus this is a 1, and we now have minus 0. I have dk plus 1 dk plus 2. The dk plus 1 is the k plus 1th digit, then the k plus 2th digits, and so on and so forth. This dk plus 3 and so on. So wherever this decimal places stop, so we have times 10 to the power of minus k. So if we go ahead to analyze this, there's no way we can actually solve it without making some assumptions. So this is n asterisk minus n. Okay, we still remember this is our absolute error. So our absolute error is equal to, so I'm now going to make some assumptions at this particular point. So just flow with me as we dive in together. Now remember that we are working with dk plus 1, is that okay? Greater than or equal to 5, is that okay? So I'm now going to ask myself, look at this difference. Okay, what is the maximum value of this difference? Because this is our absolute error, so the maximum value of this difference will give me the maximum absolute error I can actually have whenever I round up a number to k decimal places. I'll take that again. The maximum difference that can emerge from this particular number is corresponding to the maximum absolute error that I can have. Do you understand? The maximum absolute error I can have. So I need to find the smallest number. If you want to find the maximum number that you can get from a difference, when you're doing the decimal part, you have to look for the smallest decimal that you can take away from 1, so that you have the maximum difference. Like for instance, if I want to find the maximum difference that I can obtain from a decimal, for instance, that a 2 decimal number that starts with a 9, 0.9, so I might probably consider it as the smallest difference, right? Smallest difference I can get from this particular number, since it's 2 decimal place, is 0.90. Do you understand? 0.90, and this should give me a 0.1. But see what happens if I start increasing it. 0.91, if I increase this particular place, and you get a 0.09. You understand? So at this particular first scenario over here, what we just evaluated was the biggest difference that we can get by subtracting a 2 decimal place number, such that the first digit is 9. So the highest difference that we can get when we subtract a 2 decimal place number, okay, so that the first digit is 9, and you have to be careful in the choice of your second digit. In the choice of my second digit, I have to choose the smallest one. Okay, in fact, the general case for choosing the decimal number, if you want to get the maximum difference is that you have to make sure that the decimal number is the smallest of that particular scenario. Okay, so that's what we are trying to recreate in this particular place. If the decimal keeps growing in size, then the difference you will get will be reducing. Imagine I'm doing 0.95, I'm going to be getting a 0.05. okay, so but what I want is the max, and that's what I want to get from this particular place. So I want it to be that this decimal digits, the decimal part, the Mantiza part, starts with a 5. And since these decimal numbers, the dk plus 2, keep prolonging, so I don't know when it will stop, so I can assume that the smallest version of this particular decimal number will be the first number bigger than 5. Who can picture the first number bigger than 5? Nobody can actually picture it, but we'll assume that the first number bigger than 5 is if it's a number such that we have 5.000000, and after infinite number of zeros we now have 1. So that's what I'm trying to represent here. So this is a 5, and I have 0, 0, 0, infinite numbers of zeros, then I now have a 1 at the end eventually, or something like this, times 10 raised to the power of minus k. Okay guys, now we have gotten to a point where we need to apply another logic. Now when you subtract this particular, remember it's the smallest decimal number that starts with 5 that we can actually ever come up with. Okay, when you subtract this smallest decimal from 1, what you're going to get, just like I've been trying to say, is you're going to get a maximum possible representation of the difference between the approximated version of the number n and the actual version of that number n. So what they are just trying to tell us in essence is that I don't need to use equal to here again. I'm going to use a less than or equal to. So whatever I get in this particular place, whatever the difference I get between this particular number, since I've chosen here to be the smallest decimal number that I can actually picture, starting with 5, then 1 minus that smallest decimal number is always going to give me the maximum difference between this particular two. So since it's the maximum difference, on no occasion should the difference be between this and this be greater. Is that okay? Since something is maximum, so whatever the outcome of the left hand side is, at worst it can be equal to the right hand side, but it can never be greater than it. So it's usually a convention for us to represent, change this equal to at this point to a less or equal to or a less than, because you're trying to say that the outcome of this particular difference here is the highest possible difference that I can ever obtain by subtracting these two values together. And if we subtract these two values together, we'll get a 0.499999, infinite numbers of 9s, until we get to the last 9 possible. This 9 is somewhere at infinity, then times 10 to the power of minus k. So we'll now have our absolute difference is going to be less or equal to, so this is the maximum value, max. So this is going to be what, if you approximate this, you get a 0.5, and since it's an absolute value sign, you can just write the 0.5 without any signs, then times 10 to the power of minus k. So this is where we get that theory, because when you take the difference between an approximate value and actual value, this is actually an absolute error. Is that okay? So this is absolute error. So absolute error is less or equal to 0.5 times 10 to the power of minus k. And this particular expression, okay, is what you are going to be using to solve a lot of error problems. We call it greatest possible error, or greatest possible approximation error. So the greatest possible approximation error. So the greatest possible approximation error, or greatest possible absolute error that we can get, is guided by this particular equation. So whenever we round up a decimal number to k decimal places, okay, this is at best the highest error that we can get, and the error is actually dependent on the number of decimal places of k. So this is actually the theoretical analogy to solving this particular problem. In subsequent videos, I'll try to explain this same concept with simpler words, but just for those of you who wanted to know the theory of how everything came about, so this is just a rough sketch of how it came about. So I hope you've learned something from this video. Please like and subscribe and share. Hit the notification bell to stay updated. So I'll be saying bye for now. See you in the next video.